So our speaker tonight, I'm just going to do a quick introduction. Saraj Munjal is a senior software engineer at Robinhood, where he's part of the amazing storage platform team. And I think you got a couple coworkers here too, right? More members of the amazing team of Robinhood. We all love you guys. Robinhood is awesome. This is like the thing where you can kind of sort of cosplay as a trader, right? Isn't that what it is? Okay.
You are a trader, so
like anybody can. Like you don't even have to live in New York and go to the exchange or anything.
You don't have to dress.
Yeah, exactly. Yeah, you do it in your pajamas. So Saraj says he's been diving deep into the Postgres ecosystem and fighting schema migrations for more than the past 3 years. And before Robinhood, he worked on Firebase, the Firebase real-time database at Google, which helped power seamless real-time data for millions of users. And in a past life, also built large-scale Android apps for the Indian market and worked as a back-end engineer at a startup. Oh, and I gotta mention this, because you mentioned outside of the tech world's an interest. Actually, I don't know, so Saraj, you said you're an ardent, you said you love embracing the outdoors, hiking, paddleboarding, doing stuff, which is, you live in Seattle.
That's table stakes,
awesome. But you also mentioned being an Arsenal fan, and I feel like I know a few people who are Arsenal fans, and nobody's just a little bit. I know it's just a little bit of an Arsenal. If they're an Arsenal fan, they're probably a fanatic. Is that your experience too?
Yeah, going on 20 years now.
Do we have more? Are there more Arsenal fanatics?
I just moved from Florida.
No.
Arsenal fan means something different. I have no idea.
Yeah, I'm actually wondering what this meeting is.
No. It's a soccer team. Okay. Yeah.
I like Manchester
Football.
United.
It's a football.
Okay.
All right. So on that note, welcome, Saraj. Thank you for coming.
Yeah. Cool. Thank you, Jeremy and Lloyd. So the intro already happened. I'm just going to skip past a bunch of things. Just a brief note. This is my first time speaking in front of an external tech audience, so I will appreciate any feedback. And yeah, thank you so much. And especially because this talk also got accepted at PGCon Seattle next month. So this is going to be a good trial run, and feedback is welcomed. So Jeremy already gave a great intro. We've basically hit everything. There's a couple of my favorite hikes in here, and we can chat more about that later. Cool, let's get started. What exactly is DDL and why are we talking about it today? DDL happens whenever we need to modify the schema of our tables or anything inside of our database. So common examples are creating and dropping tables, adding, deleting, modifying columns or constraint or indexes, and other things. But why does DDL happen? It's because even though Postgres is a relational database, the schema changes. New features will launch, new business requirements will come up, and because we're human, we'll make mistakes, and we'll have to fix our schema at some point. Let's talk about why DDL is hard to run. So most DDL statements will acquire access exclusive locks. And some statements will also run for a long time because they do table scans. Especially at scale, this problem gets a lot worse. With systems that are always online, we can't turn off traffic to the database just because we're applying DDL. So anything that we do is in parallel, and the impact is felt by users. When you run DDL on large tables with thousands of QPS, all the queries can get blocked, and the database can just stop doing any work. There's another problem area called backwards compatibility, and we are going to talk about that in detail later. So let's dive deep into the first problem area, which is long-running DDL. So most DDL statements will acquire access exclusive locks. Think about anything with alter table. And these are the most expensive locks in Postgres. They'll be acquired relatively quickly, and then if the statement is doing a lot of work, they will not get released. Luckily, many DDL statements are super quick because they are metadata only changes inside of Postgres, and they do not need to go visit all the rows in the table. A good example is alter table, add column, or alter table, rename column. So whenever this happens, we're all happy because it finishes quickly, no big deal. PS, before Postgres 11, this simple thing, alter table, add column, was a full table scan as well. But yeah, yeah, we had many incidents with that. Anyway, so sometimes we're not so lucky. So if you have tables with 100 million rows or a few billion rows, the table scan is going to take hours, even on like beefy instances. And if this instance is receiving traffic, all the queries will queue up behind the exclusive lock, and the database is not really going to do any work. The database is going to die, the connection pool is going to die, and this is basically a service outage. Some statements will do table scans, and we're going to talk about them. So create index or reindex does a table scan. We can work around it by adding the concurrently keyword, which will reduce the lock to a share update exclusive lock, which means that other writes and reads can progress. Creating any constraint like foreign key, not null, or exclusion on an existing column will also do a table scan. So we can work around this by using not valid and deferring the validation of the constraint to later. So Postgres doesn't have to go and visit every row. Another thing is alter type. This will scan the full table and rewrite it if types are not compatible with each other. And there's like very few examples of compatible types that I know of. One of them is varchar to text and vice versa. But yeah, this can be a problem. Let's walk through an example with some queries, because all of us just love looking at the Postgres terminal. We create a couple of tables, product and image, like your typical e-commerce scenario. Product has a few columns. Image has a couple of columns because you have products and then you have images. You insert a bunch of values into product and image. Just imagine that you did. Then you add a new column called image ID to the product table. This will acquire a short-lived access exclusive lock. It'll finish really quickly in a few milliseconds. Even if you have load, it's all good. And then imagine you backfilled a bunch of image IDs with some business logic. Maybe you got images from your product designer or whatever. You uploaded them to S3 and whatnot. And then you backfill all of them here. Now, if you add a foreign key constraint, this will scan every row in the images table and check if its image ID is valid with what you're inserting in the product table. This is a long exclusive lock. And this is where you add not valid and you kind of get away from it. This was it for the problems for long-running DDL. Now we're going to focus on backwards incompatible DDL. So this is a common problem in systems with migrations or schema changes tied to code, like ORMs. Common examples are Django and Rails. At any time, the application code expects the database to be in a particular state. So you have model classes, and they will expect that the database is like in the same state. I'm going to walk us through a deployment of some DDL alongside new code and how this can break. At any point, feel free to stop me and ask me questions about this. It can get a little tricky to understand. So we have a code deployment here. We have some app servers which have this model class. It has 3 columns in product, ID, name, description. And we have the database schema on our Postgres DB, which is like ID, name, and description. So it's all matching up, all good. Reads and writes from this application version are both working fine. And then we decide to deploy a new application version, which has this DDL statement. Let's look carefully at what it's doing. It's an alter table, add column, not null, and it's not providing any database level default. By itself, the statement is fine. It will require a short-lived exclusive lock. It'll run quickly. It'll not block other queries. So no long-running DDL stuff. And it finishes. We go here and we see that the database schema now has a new column. At the same time, we get a new application version because we're in ORM world and the code is connected to the department of DDL. This new app version does include the new column, image ID not null, and reads and writes from the new app version work fine. But the old model does not know about image ID, and this is a not null column. So what we'll see is that reads are still working, but writes stop working with this error. So because we are not sending anything from the old app version, and Postgres expects some value there because of not null, it's just going to fail all the writes. And if you have a low traffic service with a few QPS, you may be fine. You'll eat some errors. Whatever deployment system that you're using will slowly roll away the old version and introduce the new version, and you'll be fine. No worries. But if you're a high traffic service or a critical service which cannot take any failed requests, you have error rates now. If you have health check systems, which are common with modern deployments, such as Kubernetes and EC2 orchestrators, they will look at your metrics. They will see failures. They will want to roll your code back to the last known good state. If you do that, you're going to have even more errors because the old code doesn't really work with your database schema. And now it's a common question. Can you roll back the schema change as well? The answer is, in this case, you cannot, because it has already taken writes from the new version as well. And it has user data, so you can't drop that column anymore. You're going to lose data. So things just went from bad to worse with a simple DDL statement. And you are now failing all of your writes. Any questions at this point before I move forward? Yes.
True story.
You're seeing these guys laugh in the front row?
Story singular?
Yeah, okay. So this happens. Cool. This was one example of a backwards incompatible operation. There's many more. If you add a not null constraint and your app is still writing a null from somewhere, the same thing's going to happen. All those writes are going to fail. If you drop a column or rename a column, the old version doesn't know about it, obviously. It's still going to be a problem. If you're altering a column, same thing. Type transitions are, if they're not binary coercible, it's going to be a problem because your writes are going to stop. And contracting an enums value set. So like with enum types, if you've disallowed some prior values for the enum, again, your writes are going to stop working. At this point, I'm going to address some frequently asked questions up front. Why can't you just stop the old version of the app and execute DDL and then start traffic back up again? Simple answer, because we're trying to be always online, we cannot shut traffic off. Why do you execute your DDL and deploy new code at the same time? Why can't you have somebody do it on the weekends? Because this is a very manual thing. And if you have hundreds of microservices, hundreds of small applications running, you have to automate it. We use Django and Golang at Robinhood. And these frameworks will, Django and Golang plus SQL C, which is the framework, these will generate DDL changes according to new code. And these are deployed together automatically in a custom CI pipeline that we have. Why do you deploy DDL first and then new code? Why can't you do it the other way around? It's a good question. Some people do it, but with our technology stack, it's extremely hard for us to do. Django, Rails, and the Go ecosystem we use, all of these assume that you deploy your DDL first before the new version of code starts running. Yeah, so that was it about discovering the problems. Now we can talk about how we fix them. For long running DDL, just kill it with kindness. We have a runtime strategy. So at runtime, we're running DDL. We will be very cautious. We will set a statement timeout at 10 seconds, a lock timeout at 10 seconds. What does this mean? If the statement is waiting for a lock that somebody else is holding on to, it's going to kill itself within 10 seconds with the lock timeout. If the statement did get the lock, it's doing its work, and for some reason it was long running, it's doing a table scan, it's going to still kill itself in 10 seconds because of the statement timeout. Another safeguard that we added is we grab a manual share update exclusive lock on the table. So this is kind of a watermark for how hot the table is running. If we can't get a share update exclusive lock within a particular time period, that means it's a lot of writes. And if we were to execute a DDL with access exclusive lock, it's going to cause a lot of impact. So if we can't do this, then we just fail and don't proceed with the DDL. Some of our apps are Golang, and Golang has really nice support for context timeouts. So client itself, we can cancel all the queries that it's running after a particular time. We don't really need to deal with statement and lock timeout. So this was about timeouts. Also run DDL transactionally and retry it on failure later. This is a really nice feature of Postgres, in my opinion, one of my favorite features, that DDL is transactional. This makes it safe to retry whenever things fail. Like even if you were doing 5 things in a single transaction, because it's transactional, fails, you can just retry it later, no big deal. There are some exceptions to this rule. Create index concurrently is a common one. We talked about that earlier. Alter type, add value, basically expand an enum. These cannot run inside of a transaction by design in Postgres. So for these, we skip the timeouts. And if we see failures, we do manual intervention. We'll go and clean up the state later. But we want to try to catch all of these cases before they make it to production. So we try to do static analysis with linters on all our microservices. Oh, is it back? Okay, great. Yeah. So static analysis on all our microservices. And why is this happening? Oh, sorry, folks. I'm just going to plug it in again. It's not been a good day for technical issues. Okay, cool. So static analysis, and we have patterns identified already. If we can get your SQL, which is kind of a hard problem with Django, if we can get your SQL, we will warn you about potentially long-running statements because they're going to do table scans. We also have mandatory code reviews for our critical customers. And we will kind of handhold them through alternate paths. So like not valid for constraints, concurrent index creation, done manually, and then synchronized later through like migration and Django. And our threshold for this is 500K rows. If your table is larger than 500K rows, that is when we get into, oh, okay, this is going to be a little risky, so we're going to take manual action. The timeout stuff that I talked about is a little bit tricky to implement, and this is because of our architecture. I think this is a fairly common pattern. People use like a PG bouncer proxy in front of their database in transaction mode, because this is how you can get the maximum throughput out of it. And we have this application container and a sidecar, which is like just another PG bouncer binary running here for a client-side connection tool. And this is how the traffic flows. But if you try to set statement timeout or log timeout or any other session level parameter, it's not going to work because you're balancing your pool at the transaction level. So the fix we had for this is we added a small DDL PG bouncer, which we talk to directly without going through the sidecar. It's running in session pooling mode, has a really small pool. And the rest of the application traffic, regular reads and writes, run through the regular PG bouncer. Cool, this was it. And for backwards compatibility, we got to just test really hard. With backwards compatibility, it's a hard problem to catch because you have two application versions, both of them expect some database state. And if you run unit tests or spin up the database in Docker and test against them individually, they're going to pass because everything is fine. We also tried doing linters and static validation here. It didn't help much because we don't have enough info about the old state of the application. Sorry. So we tried a really ambitious thing. We wanted to run all tests on the old version of the app against a newer version of the database schema. So you would get the same error messages as you get in production because you've kind of reproduced that state in a test environment. To do this, we would need to put test artifacts into Docker images and run them against a Postgres Docker container with the newer schema. This worked in theory, but we realized that it's extremely tough to maintain Docker images for Python and Django environments with our Bazel stack. So Bazel is like this packaging and test running toolchain that's fairly common now. And eventually we realized that we were re-implementing parts of the test toolchain, parts of Bazel, which is not something that we wanted to do, and it doesn't scale to hundreds of services. So this is too complex. What do we do? And we realized that we need a bare minimum set of information, which is what does the model think and what is the database state according to the model in both the old and the new version. So we came up with something called schema state. We generate a schema state JSON file representing model state, DB state for both the old and new versions of the app. Each app commit has a single schema state file, which is also pushed to a remote metadata store. Whenever somebody generates a new migration locally using Django or Golang tooling, we will update the schema state, generate a new one, and we will test it against the last known good schema state. And we apply certain rules, all the rules that we know where backwards compatibility is going to be a problem. Failures here will trigger manual code reviews, and that's where our team will jump on and help teams fix or work around. And successfully tested code will proceed to land and then go into production. And we will also then update our source of truth, which is the last good state of the schema state. Here is an example. I don't know if I can zoom in further, but I hope people are able to see stuff. So for every table, like product that we talked about, we collect a bunch of information for every column. So this is like a map of maps. For every column inside every table, we collect model info and DB info. So the type in the model info is the language's data type for this field. So it could be string for Golang or str for Python, etc. We see if the model thinks that it is nullable. There are application level defaults in some frameworks like Django. And we have an ignored field, which can help us drop columns safely without running into compatibility issues. There's also a bunch of information at the database level. So the type of the field in Postgres, if the column is nullable, if it has a default value declared, and then a bunch of metadata about sizes for different types of fields. All of this information is from the PG information schema columns. And we also have enum values, which is my favorite. And we have this kind of JSON duplicated for all columns, for all tables. So it's like a decently big JSON, but a few kilobytes. And how it gets used, I'm just going to skip a slide here, is like this. So remember our old product schema and the new product schema in the example for compatibility? So this would have an old schema state for the old commit, which is in the metadata store. And when we generate the new migration and generate a new schema state and pass it to CI, this would just fail the test with the missing default value. And this commit would never make it to production. It would never get deployed. The DDL would never get run, and it's all good. Here's some of the rules that we encode. So this is our example from earlier. If you're adding a column with not null at the database level, it must have a database level default. Enum values cannot be dropped at the database level. Your set of enums can only expand. Dropping a column on the database is not allowed unless the older version's model is setting it to ignored. Changing the field on the database, changing the type of the field, which is like an alter type, is allowed only for varchar to text. Everything else is risky. And when rules break, we work around the problem. For example, alter type and rename can be done by adding new columns with whatever update you want, backfilling from the old columns, and then safely dropping the old ones. So like expand and contract. Yeah, and this is basically how we solved this problem. And the results are pretty good. The simple backcompat tests have worked great. No real issues with any customers yet, and this is widely deployed. We still see the occasional long-running DDL. Long-running DDL is like a pervasive problem in Postgres, and we keep discovering the occasional new cases. Like we were changing a varchar column size, increasing it once, and like to best of our knowledge, it does not cause a table scan, but it did, and the timeouts got it, and it was all safe. But we found out that this is an edge case in Postgres where if this column has a conditional index using the any operator, this is going to do a table scan. It's rewriting the index underneath. Yeah, we never expected it, but it's fine. Things break. So, and our ORMs will do complicated, wacky things all the time, which is why the runtime safeguards help. And also, manual review is still plugging in a lot of holes. We've come a long way from having many incidents in the past. It's gotten a lot better. And we'll continue investing in this work because we'll keep discovering new backcompat rules and we'll support newer clients. We currently support Django and SQL C with Golang, which is most of our wheelhouse. But yeah, we'll keep going. So thank you so much. This was it for today. And please reach out with any questions or feedback. There are some social links on the slides, and I'll share these later. So thank you. Okay, any questions? Yes, Ben.
Yeah, I had a question about the PG bouncer stuff where you had a different PG bouncer for DDL.
Yeah.
Why do you do that instead of just having a different user for DDL, the same PG bouncer, but then set that to session mode?
We can do that as well. Yeah.
Okay.
Yeah.
And then also, so we have solved this problem by having post and pre-deploy migrations.
Yeah.
Can you guys not do that, or am I missing something? This feels much more complex than just having post and pre-deploys.
What part of it is it like the
making the JSON file feels like a thing you have to do so you don't have errors, so you can catch your errors.
Right.
But if you just make handcrafted DDL before and after to run before and after your code deploy, then you can get through all the same problems too.
I think you may still have some of them, to the best of my knowledge. Like I know PG role does this, the same thing that you're talking about from Zeta. It's like a new library, and I think there still might be a few cases, but yeah, maybe it'll work. So I think it's really hard for us to do, especially with Django. We basically have to going to split every change and redo all the Django tooling. So that's the hard part. Yep.
Can you describe the pre and post deploy methodology a bit more for anybody who's not familiar with it?
Yeah, so you kind of split the migration into two parts. So for example, if you wanted to do a rename, then you would create a new table with the new name and shadow traffic to it using views or triggers or something. And then in your post deploy, you would do a cutover. So when the new version is done deploying, it forces a post deploy step and you cut over to whatever you want to do. So it's kind of shadowing traffic either through views or through copied tables. So yeah, for a lot of this stuff, I think that approach is expensive. I have not tried the view approach. It is relatively recent. So I saw this again with PG Roll from the company's data. Before this, we have tried triggers and we have also tried logical replication for creating new copied tables with the DDL applied and then shadowing writes and then cutting over. Both of these approaches were a little tricky to execute at scale. So when you have like really big tables, and especially if you're running with not a lot of headroom, you end up doubling your disk size, you end up doubling your IOPS for those tables. So it's operationally risky land. So like if I can just cache these changes on the left and not have to do them and take the risk on, then I think that's a good approach. Yeah. Cool. Any other questions? Yeah, go ahead. Oh, sorry.
So I'm not a Postgres expert. I'm probably gonna get some terminology wrong here, but have you guys actually experimented with the storage engine and like physical modeling of the tables, like how they're actually written in bed for the disks? And if so, is there anything you can do there to help with these expensive DDL operations?
It's a great question. We cannot do any of that. We use like Amazon RDS, so that's not in our control.
Now, I will say that Postgres has exposed the stuff so that you can change the storage engines in Postgres. So there are people who are writing other storage engines for Postgres that don't use the write-ahead log, but and do stuff differently, or column-based storage engines for doing more analytics. So you can do these, add these storage engines in, and then on a per table basis, you can change the storage engine. So you can have one table normal storage, one table column storage, one table that's doing an undo log instead of a wall log file, and have different styles. A lot of these are in development, and I wouldn't run them in a production system yet. That's why you don't see Amazon doing it. But Amazon Aurora is a real good example of where they've changed out the storage engine. And they're using their own custom-built storage engine, basically. Theirs is probably more complex than that. I'm simplifying it. But yes, that's a great example of where you've changed out the storage engine.
Okay, Eric.
So a little trick that I'm doing with my apps for the matching the app with the proper version of the schema.
Mm-hmm.
So every app, when it sets up the connection, I have one table with one field where I have a UUID in it. And then the code that generates the migration scripts will actually also brand that UUID field with a new value. Mm-hmm. And that value is actually as a constant, like a .h include file into your program, so that when the application starts, the first thing it does, when the first connection does, do I have a version of my schema where I have the same ID that I'm expecting? So at least I'm not going to be starting to run older or ahead versions with the schema. Now, it's a trick that at least will reduce most of the problem, especially when you have a cascading effect that you relaunch a new app, and at least the app will start the connection and then shut down instead of crashing everywhere. So that's a little trick, that's one. The second trick is that I found myself creating a lot of stored functions to buffer my edits. So instead of having the app to the ORM actually write to the file, make a request to change, if I do it store functions can also be part of the DDL process. So at least if you have a store function which has a version number in it or some mechanism, then if there is a change that occurs, your store function become the intermediary between your application and your database. Those two techniques can help.
Mhm. Yeah, that's a good idea to buffer writes, and it will definitely protect a lot of the write failures in case something like this happens. Yeah, that's a good one. I know that. Thank you. Yeah.
I had another question with the timeouts.
Mhm.
Do you find that you have lots of problems where on a bit system you just have to keep retrying again and again because things keep timing out?
Yes.
That feels like a problem with that.
Yes, sometimes we just have to wait for the time of low traffic. Like we look at historical data, we figure out, okay, this is a time when there's historically been low writes to this table, maybe overnight, maybe over the weekend, and probably, I don't know, 1 or 2 cases every month, it has to work like that.
Okay. Because in your problem statement, right, it was like we have these things that run all the time. We
Yeah.
have to do something.
Yeah,
Just
so-
wait for a time when it's not right.
Yeah, and for those things, you sometimes have to queue the application code change for those times as well. Yeah. So I don't think there's any way around that, really. You can,
I mean, backfills are usually what we do to get around it, right?
Yeah,
have
so
some
you-
kind of long backfilling thing.
exactly, yeah. And then you have the problem where you have twice the amount of data.
Yep.
So kind of works, but for super large tables, that approach is also a little bit risky. Yeah. You need to be running your DBs with a lot of headroom for that stuff. So, cool. All right, no more questions. Thank you. Yeah.
Cool, thanks.